So basically this is um, a simple vacuum simulation tool developed by Leybold vacuum people. So here we can define various things. So I have taken a simple system where this is my chamber, and it is the particles in it is pumped down by um, a backing pump, trivac, and a turbomolecular pump with a maximum pump speed of 250 liters per second. So these are the parameters I have defined. Starting pressure, always let's have it 1 bar, which is 1000 millibar. Target pressure, let me take it down to 10 power minus 2 millibar. I'm assuming the chamber volume to be 50 liters. Now desorption rate is fixed for various chamber material. So for a stainless steel it is 10 power minus 6 millibar liters per second centimeter square. It's fixed one. It is seen here. For different materials we have different values, so I've taken 10 power minus 6 for stainless steel. Now leak has to be defined. It is dependent on the orifice size, the size of the leak. So let's have it 10 power minus 2 initially, which is a very small leak. 10 power minus 2 millibar liter per second corresponds to a 0.01 mm orifice. So if that is the case, we will check what is the maximum pump speed achieved, whether such a vacuum can be created and everything. So I'm just giving calculate. So now the time required to pump down and the maximum pump speed that can be achieved has come out. So let's check out the speed curve. So the maximum pumping speed that can be achieved for this case is 703.89 meter cube per hour. Now if I want to know the corresponding value in liters per second, I can convert it. It is close to 200 liters per second. So that could be the maximum pumping speed achieved. And will we be able to achieve 10 power minus 2? That can also be figured out. So calculate pump down. We will do that calculation. And success in the sense we can able to achieve the destination pressure, which is 10 power minus 2. We can achieve 10 power minus 2 at about say 3500 seconds. It is possible. So whatever we have defined is a realistic condition. It is possible. 10 power minus 2 millibar vacuum is possible if our leak size is 0.01 mm. Now what I am going to do, I will be increasing the leak size to 1 mm. So for 1 mm the leak value is 1 millibar. It will be increasing by 2 orders. For every 1 order in increase in orifice diameter, the leak value will be increasing by 2 orders. So 1 millibar liter per second is the leak value for 1 mm, no, 0.1 mm orifice. Let's check whether with 0.1 mm orifice the same 10 power minus 2 millibar is achievable or not. So I am going to check the maximum pumping speed. So if you look the value, it is only 8.94 meter cube per hour. So if I have to find out the value when liters per second. It is just 2 liters per second. This is all it can achieve. So even though our pump can pump up to 250 liters per second, the maximum pumping speed that can be achievable is just 2 liters per second. The efficiency is highly coming down because of the increase in the leak size. Now this is the reason we say we should not switch on the turbo pump, because it cannot pump down with its fullest efficiency. Though it can pump down up to 250 liters per second, it can only handle up to 2 liters per second because of the increase in size. So I am also increasing the target pressure. I am not giving so if you look at the pump down curve, it says failed. So what it is saying is whatever pressure you have given is not a realistic value. For 10 power minus 2 millibar vacuum cannot be achieved with 0.1 mm orifice, even though you put a heavy turbo pump which can pump up to 250 liters per second. So it says that you cannot achieve it. It says failed. Now why it is failed? It says target pressure not reachable for optimistic result, for pessimistic result. However you are be it optimistic or pessimistic, you cannot achieve it. So what we do, we will increase the target pressure to 1 millibar and then we will check. Yeah, success. So 1 millibar is achievable. So because we have increased the orifice size, now we can only achieve a vacuum of 1 millibar, because the pumping speed maximum it can take out is 2 liters per second. Further, we will increase the orifice size from 0.1 mm. Now we will increase to 1 mm. That is our case. For 1 mm, leak value will increase by 2 orders. So it will become 100. So we will check out whether such a case is possible. If 1 mm orifice is there, can we achieve a target pressure of 1 millibar? We will check out. So we'll check the maximum pumping speed possible. It's only 8.58 meter cube per hour. Close to that. It's again 2 liters per second. That's all it can pump down. And we will check whether we can achieve 1 millibar vacuum. Is it possible? Failed. Which means it's not possible. Target pressure is not reachable. So we cannot achieve 1 millibar vacuum even if the leak size is 1 mm, even if we pump down with a turbo molecular pump. Now that's the reason why we need to go for 2 chambers, where in the first chamber we will bring down to 1 millibar, then we will go down further. So if I increase the target pressure further by 2 orders, 100 millibar, and then we will check whether it's possible or not. Yes, it's possible. We can only achieve a vacuum of 100 millibar with a leak size of 1 mm. This is all possible, and we are really seeing it in the experiments. When we are pumping down with a rotary pump for 1 mm orifice, we can reach up to only 100 millibar, and when we put in argon, it's saying all confusing values, 10 millibar and everything. We cannot believe that, but without putting argon, it says 100 millibar, and it's true. And as per the simulation, Leybold simulation, it's saying it's true. We can only achieve 100 millibar vacuum with 1 mm orifice. We cannot even go down up to 1 millibar. So probably this is a simple simulation. Probably they are using very simple equations as the background equations to do it, but we can rely on this because these guys are actually building a lot of vacuum systems. So whatever simulation tool they are giving out should be a realistic value which is matching with our experiments. Yeah.